We all worry a little about our batteries, right? That they might overheat or worse. Well, get this. A new research paper just dropped, and it shows how a really cool concept from math, we're talking fractals, might just solve one of the biggest dangers lurking inside every device we own. So let's dive in and see how this amazing geometry could stop batteries from exploding. But before we get to the solution, we've got to understand the problem. So what is this massive thread hiding inside something so small? What's the tiny little thing that can make a battery fail, catch on fire, or even, explode? Okay, so it all comes down to this tiny, microscopic villain, a little troublemaker that grows silently inside our batteries every single time we charge them up. And let's be real, lithium-ion batteries are literally everywhere. I mean, think about it. They're in your phone, your laptop, and electric cars. They're even in satellites way up in space. So yeah, the stakes for making these things safer and more reliable, they are huge. So what is this little villain? Well, it has a name, the lithium dendrite. Just picture these tiny, super sharp, needle-like things made of metal just growing inside your battery every single time you charge it. And the worst part? It's just a natural part of how these batteries work. It's the absolute root of the problem. And this is exactly why they're so dangerous. The research paper puts it perfectly. These sharp little things can actually puncture the barrier that separates the two sides of the battery. And once that happens, you get a short circuit. And that can lead to, well, fire and explosions. It's a total disaster. So what do we do? Well, what if the answer isn't to fight these things directly, but to completely change the battlefield they grow on? And this, my friends, is where our hero comes in. An unexpected hero from the world of math, fractals. Think of it as nature's own infinite geometry. All right, so here's the big idea. You've got your standard battery electrode, which is basically a simple flat surface. The problem is it's not very efficient. Energy can build up in certain hot spots, and guess what loves to grow in those hot spots? Yep, dendrites. But a fractal electrode? Whoa, that's a different beast entirely. Instead of a flat road, think of it like a super complex, rugged coastline. It has a massive surface area, and with all that extra space, it can spread the energy out nice and evenly. No more hot spots. Okay, so actually building one of these fractal things in the real world? Super, super difficult. So what did the researchers do? The next best thing. They built a virtual one. They created this really powerful mathematical model to test if this whole idea would even work. And to make the model work, they focused on one key number. It's called the fractal dimension, or alpha. Now don't worry, it's super simple. Just remember this. If alpha equals 1, that's your boring old flat electrode. But if alpha is less than 1, boom, you've got a complex fractal electrode. The smaller the number, the crazier the fractal pattern. All right, so the virtual stage is set. The rules are in place. It's time for the ultimate showdown. Fractals versus dendrites. Can this beautiful, complex geometry really stop those nasty little needles? Okay, I know these graphs look a little intimidating, but trust me, the story they tell is really straightforward. The colors show how many lithium ions are packed in. See the one on the top left? That's the standard electrode. It's kind of blue, a little green, not bad. But now look at the other three, the fractal ones. Wow, they are lit up with bright yellow and orange. That means way more ions packed in way more stably. The fractal design is just plain better at grabbing onto the energy. And that higher concentration does something absolutely critical. This next chart shows how much extra juice is flowing to the tip of a dendrite. See, for a dendrite to grow, it needs a big surge of energy right at its tip. But look at the lines for the fractal models. They're all low and flat. There are no energy spikes. The fractal surface is spreading that current out so evenly that it's basically starving the dendrites of the energy they need to grow. And the paper just comes right out and says it. The model proves it. Because the dendrite tips aren't getting that special treatment anymore, the whole chance of them growing in the first place just plummets. And folks, this right here, this is the knockout punch. This chart shows how much the dendrites actually grew over time. Look at that purple line for the standard electrode. It's just shooting straight up, uncontrolled growth. But the other lines, the fractal ones, they are almost perfectly flat. The growth has been stopped cold. The villain has been tamed. In fact, the growth was so small, the paper literally calls it insignificant. I mean, for all intents and purposes, the dendrite growth in the fractal models was basically zero. Nothing. Nada. So, okay, this is a super cool simulation, but what does it mean for us in the real world? Well, this isn't just a neat math puzzle. This could be a huge signpost pointing to a total revolution in how we store energy. I mean, think about the possibilities here. We're talking about safer batteries that are way less likely to catch fire, devices and electric cars that last longer on a single charge, and maybe even the ability to charge our stuff way faster without damaging the battery. All of this just from solving that one tiny problem of dendrite growth. And it all leaves you with this one last kind of mind-blowing question. For so long, we've thought the answer was perfection, perfectly smooth, simple surfaces. But what if the real secret to perfect energy storage isn't simplicity at all? What if it's embracing the exact opposite? The beautiful, chaotic, messy complexity that we see in nature everywhere we look?